Chapter 11 is about electrochemistry. To study electrochemistry, we must remember oxidation and reduction reactions. And remember that they always occur together. Oxidation and reduction reactions can be remembered by the phrase oil or rig. Oxidation is loss and reduction is gain. Here are some of the rules for assigning oxidation numbers so we can determine whether it is a reduction or an oxidation. So for elemental substances, for instance, H2, O2, aluminum, potassium, the oxidation number is 0. If it is a monoatomic ion, for instance, Mg2+, or here, P phosphorus 2,3- charge, then the charge is the oxidation number. The sum of oxidation numbers is for a neutral compound adds up to 0. So for H2O, since there is no charge associated with it, the oxidation number sums up to 0. For an ion, it adds up to this charge. For instance, we have carbonate and it's 2-. For group 1 metals, the charge is +2. For group 2, it's +2. And for aluminum, it's +3. For fluorine, it's 1-. For hydrogen is 1+, or 1- with metals and 1+ with non-metals. O2 is for oxygen always, and the others vary. We must use it kind of like a puzzle to solve for the other oxidation numbers. So the ones at the top take the highest priority, and the other ones come later. A reducing agent is a substance that reduces another substance, so its oxidation number goes up. And an oxidizing agent is a substance that oxidizes another substance, so its own oxidation number goes down. Therefore, it is reduced, but it oxidizes another substance. Half reduction method of balancing is when you try to balance a reaction by splitting it into halves. So first you have to divide the equation into two half reactions. Then balance atoms other than H and O. Balance O by adding H2O to the side that needs O. And then balance H by adding H plus to the side that needs H. Balance the net charge by adding electrons to the positively charged side. Make electron gain is equal to electron loss in the equation so that electrons can cancel out. When you add up the two equations, canceling things that are on the both sides, like products and reactants of the two equations. Add the same number of OH- to the equation as there are H+. If this is for acidic solutions. If it is acidic, you stop at step 7. But if it is basic, then you proceed to add the same number of OH- as there are H+. Then you combine H+ and OH- to form H2O, and then you can add or cancel H2O by combining the two equations. Electrochemistry is the study of redox reactions that produce or require an electric current or energy. It is a conversion of chemical into electrical energy carried out in electrochemical cells. There are two types of electrochemical cells: galvanic or voltaic cells or electrolytic cells. Galvanic cells are spontaneous and they produce electrical energy. Their sign of change in free energy is less than 0 or negative, meaning they're spontaneous. And for electrolytic cells, they're non-spontaneous, meaning the change in sign for the free energy is greater than 0 and they consume electrical energy. Oxidation and reduction are kept separate in different half cells when doing the reactions. The transition of electron takes place through an external wire, and the flow of electrons can be used to perform electrical work. Each cell contains an electrode or conductive metal, as seen in the picture with the gray metal bar and the brown metal bar, and an electrode conductive metal, and then an electrolyte solution corresponding to the metal electrode in each cell. So here I want to show what is happening in each one. So on the left-hand side, we see an oxidation where copper in the solid form goes to copper 2+, their ion aqueous plus 2-. It is an oxidation and it produces electrons. It's breaking things down. It's a loss of electrons, so it's becoming smaller. And it has anions coming to it because it is an anode, and it's negatively charged. We can remember that the anode has oxidation happening to it by the phrase anox. Anodes have oxidation happening to them. The next half cell, the one to the right, is a reduction half cell in the blue water, where silver aqueous adds electrons to become silver solid. And here we can see the reduction is happening here, and the reduction is gain of electrons. So by gaining electrons, the silver becomes a solid. It consumes electrons, and it is a cation. Cations go to the cathode, and it is positively charged. Here we can see a red cat, as to remember that red cat, to remember that reduction happens at the cathode, and also that cations migrate to the cathode. The anode is made up of the metal reactant that is oxidized. So here we can see the anode where copper solid starts and is broken down into copper ions. Then the cathode is made up of the metal that is produced by the reaction. So we see that silver solid is produced by the reaction. When there are no conductive metals involved in the process, an inert electrode is used. That means it does not participate in the reaction but provides a surface for transfer of electrons to take place. Some examples include carbon graphite or potassium solid that are often used. A salt bridge is a U-shaped tube with agar saturated with strong electrolytes. Electrolytes are composed of ions not involved in cell reactions. For example, sodium nitrate. Electrolyte flows in to neutralize the charge buildup in the half cells. Anions from the electrolyte migrate to the anode to replace the negative charges that are as the electrons are flowing out. And the cations have cathodes replaced to them to again balance out the charges. And electrons flow from the anode to the cathode. The cell reaction is an overall reaction that takes place in a voltaic cell. They combine individual half-cell reactions, and the number of electron gain should equal the number of electron loss. Electrochemical cell notation. And anode oxidation is always on the left side and cathode reduction is on the right. A good way to remember this is that the reaction goes from A to C, or kind of like in the alphabet, and the two dashed lines separate a salt bridge, like the anode and the cathode side being separated by salt bridges, and the one slash separates different phases. For instance, aqueous to liquid, or liquid to gas, or to solid, and so on and so forth. Comma shows that multiple electrolytes are used. So an example of this is anode, one line, electrolyte, two lines to show now we're transitioning to the cathode, electrolyte again, one line, cathode. So one way to verify this is that at the end of the reaction, both solids should be at the end and at the beginning. And that, whether it is coming from a inert cell or inert electrode, or coming from the what is produced at each half cell. If no conductive metal is again at the anode or cathode, write a slash and then the inert electrode. For instance, carbon graphite or potassium solid. Standard cell potential is the cell potential at standard conditions. For this, it is important to remember what standard conditions are. It is when temperature is 25 degrees Celsius and the concentration of dissolved substances is 1 m and the pressure of all gases is 1 atm. The calculating the standard cell potential is E cell is equal to standard reduction potential of substances reduced minus the standard reduction potential of substances oxidized. Subtraction is already included, so don't switch the signs. Standard hydrogen electrode. It serves as a reference because it has a potential 0 voltage. We can see this here in the hydrogen gas molecule. H2 gas at 1 atm pressure. The concentration is 1 m, and the PT, or platinum, is electrode, and the temperature is 25 degrees Celsius. We can use a voltmeter to obtain a positive meter reading, then attach the electrode to the negative meter terminal, which is the anode that goes through the oxidation. So anodes are negative because they go through a loss of electrons, and they are initially negative to begin with. And electrodes are attached to the positive meter terminal is the cathode, and it goes through a reduction. And initially, it does not have many electrodes because, as we can see here, the copper is aqueous and it is not a metal yet, so it doesn't have many electrodes and it's positive in the beginning. Table of standard reduction potentials is the standard electrode reduction potential, E with a circle. Always refer to the half refractions as reduction. And the table, at the top of the table, the E values are more positive because there is a greater attraction to electrons, meaning they're willing to be reduced or gain electrons. They're easier to reduce. And at the bottom of the table, we have less positive E values and there's a greater repulsion to electrons, and that's why they are willing to donate or be oxidized. When the half reaction is reversed, the sign of E is also reversed. But when the half reaction is multiplied by any integer, the value of E remains the same. We're predicting a spontaneous reaction. For the reaction takes place as written. For the reduction, the reaction takes place as written, and the reduction is the one with the more positive E standard value. And we know this because at the top of the table, the values of the half reactions are easier to reduce. So that's why it stays in place and it is a more positive value. For oxidation, it is a less positive value and you reverse the direction of E. The number of electrons gained should equal the number of electrons lost, and you have to balance it out in this way. So calculating the standard cell potential means that we have to go E cell is equal to the E cathode minus E anode, and E cell is E reduced minus E oxidized. Again, at the anode oxidation happens, and at the cathode reduction happens. Red cat and anox are ways to remember this. To calculate this, when a cell reaction is given, identify the oxidation and reduction by writing down the oxidation and reduction values. Then get the E cell values from the table and then apply the equation using those values. But when just given the half reaction and given the E cell values, use the more positive values as reduction and then just apply to the equation. So therefore, when the values of E are given, the equation is much easier. But when just the equation is given, we have to apply it and understand what is being reduced and what is being oxidized. The relationship between G, K, and E cell. So from going from G to K, we already know that it's that change in free energy is equal to minus RT ln K. But when going from G to E cell, it is change in free energy minus N, which is the number of electrons, times F times E cell. And F is Faraday's constant. It is 96,500. And when going from E cell to K, the equation is E cell is equal to RT over NF ln K. Again, N is the number of transferred electrons, R is 8.314, and T is in kelvins. At spontaneous reactions, we already know that the free energy should be negative, but the E cell, in contrast, is positive, and at non-spontaneous reactions, the G value should be positive and the E cell is negative. I like to remember this as a crisscross, meaning that as one goes up, the other goes down, and they don't go up together. Or you can remember that E cell values correspond to maybe the S values, where spontaneous is positive and non-spontaneous is negative. Nernst's equation. E cell at non-standard conditions can be calculated using the Nernst equation. So E cell is equal to E standard cells minus RT over NF ln Q. So E cell is, again, how we calculated E cell reduced minus E cell oxidized. R is 8.314, T is temperature in kelvins, N is the number of electrons transferred, F is Faraday's constant, and ln Q must be calculated as we have done before. Find N, the number of electrons transferred, find Q, where solids and liquids are not included, and then plug it in. Again, Q is in molarity or in M. When Q is equal to 1, the reaction is at standard state because ln of Q or ln of 1 is equal to 0. And we know that the E cell value is equal to E cell value at standard state, which makes sense. And when Q is less than 1, we know that the E cell value is greater than E cell at the standard state. When Q is greater than 1, then ln Q is greater than 0, and the E cell value is less than the E cell value at standard conditions. When Q is equal to K, the reaction is at equilibrium, and the E cell value is equal to 0. A good way to remember this relationship is that ln of something makes it go the inverse. So if the ln of Q value is large, then the E cell value is small, and vice versa. When the reaction is at equilibrium, E cell is equal to 0 is important to remember. Okay. Looking at voltaic and electrolytic cell. A voltaic cell, as we talked about, produces electrical energy, is spontaneous when the G value is negative, or free energy, change in free energy is negative, and the E cell is positive. In contrast, electrolytic cell consumes energy, is non-spontaneous, and the change in free energy is is greater than 0, and E cell is less than 0. And initially, at the voltaic cell, the charge is positive at the cathode, meaning the cathode is where the oxidation where the reduction is happening and the electrons are gained. So after the reaction has taken place, when the electrons have been gained, the charge is negative. And again, at the anode, the charge is negative, meaning there is an oxidation happening and the electrons have not been lost yet, so it's negative initially, and then after that it's positive. And it's easy to remember that electrons flow from anode to cathode. Electrolytic cell is an electrochemical cell that uses external electrical current to drive a non-spontaneous reaction. It is used to decompose a compound into its elements. Cations are reduced to metal elements. So initially, when we saw that cations, where the reduction takes place, we saw how a metal was created, a solid metal, or an inert metal. But here we see that it's inversely broken down into metal elements. And now at the anions, where reduction takes place, initially we saw that a metal was created, but now it's been oxidized to non-metal elements. So for instance, and oxidation happens. Now covering electrolytic cells. Again, an electrochemical cell that uses external electrical current to drive a non-spontaneous reaction, as we learned above. It is used to decompose a compound into its elements. Previously, and this means that the E cell value is multiplied by -1 and the reaction is inverse for electrolytic cells, what would be happening at a voltaic cell. And the cations are reduced to metal elements and the anions are oxidized to non-metal elements. The less positive electrode has an oxidation anode occur first, and the more positive has a reduction cathode occur first. And it's important to remember that. Stoichiometry of electrolysis. 1 mole of electron is equal to the charge of 96 coulombs, and 1 coulomb is the SI unit of charge, and a coulomb is ampere times second, and this is SI unit of electrical current. A moles of substance of electrolytes can be calculated using moles is equal to I, which is the current, times time divided by the number of electrons transferred times Faraday's constant. IT and F is it, and Q is charge, which is I times T, and the moles is Q, which is IT over NF.